Okay, let's get this started. My name is Aaron Wallace. I'm a master's student at Virginia Tech University. I'm working on my master's project where I'm using SPARTA to do direct simulation Monte Carlo for rarefied gas flows. There's two examples I've already posted. They were both taken directly from Bird's textbook for 1D cases. This will be my third example, and it's going to be a two-dimensional case. And it's coming from a journal article that I will put in the description where the authors used Sparta to mimic some of the experimental results in some of the benchmark cases that are used to evaluate simulators. But anyway, let me go ahead and get started talking about the problem. It's a 2D problem, and what it is it's a flat plate, and that is going, I believe it's hypersonic, but it's the velocity is 1,500 meters per second that the air is flying by or not the air, but the nitrogen is flying by the flat plate. And so I'll just start here at the top. So we're going to be saying it's quasi 2D because Sparta kind of looks at everything as you still have to put in a third dimension, but we will be telling Sparta that this is a 2D problem. You can see the Kutza number here and the free stream mean path. All this information comes directly from the text of the journal article. The plate length is 100 millimeters. The plate thickness is 5 millimeters. The molecular weight of N2 is given in the article. We're going to be using a variable hard sphere model. That's what they used in the journal article. This is the molecular diameter, the viscosity index, omega. Here, the reference temperature, the rotational degrees of freedom. Like I said, the free stream velocity of the flow is going to be 1,504 meters per second, and the free stream temperature is going to be 13.32 Kelvin. All right, over on this other side, the number density is 3.716 e to the 20. The surface wall temperature is 290. The surface collision type is diffuse. They describe their grid sizes in shape as rectangular, and this is the grid dimensions. All right, so the domain size in the x direction is 180 millimeters. The domain size in the y direction is 205 millimeters. All right, so when you break all that up with their grid size, the total number of cells is going to be 140. I believe that may be wrong. I'll have to look. We'll look when we get into the thing. It may be 14,000 or it may be 147,000. I can't remember. All right, the time step size is 3.102 e to the negative 7. You got 10 particles per cell is what they initialize it at. All right, they're doing 8,000 time steps that they're calling the transient time steps, and then they're doing 4,000 where they're considering it steady state, and that's when they're doing their sampling. He also said they're going to started the flow in a vacuum. All right, so let's go and look at the Sparta scripts that we'll be using. You see I've already run this. It takes somewhere between 30 minutes and an hour to run at this case. All right, so we'll start with the species script. And we can see here we're using the numbers that they used. And this is another key point that we need to look at while we're here is inside of Sparta, when you download it, it comes with other information right here in this data section. And here in this data section, you can pull up the air species, and it gives you a list of all the normal things that are used in air. And so here you can see that the nitrogen is laid out exactly the same way I've got nitrogen laid out in my script. It comes in because they talk about the molecular weight and the molecular mass and the degrees of freedom, rotational degrees of freedom in the article, but they never mention this rotational relation. And so I looked up and used what they had for the rotational relation in the Sparta data. So that's where I came up with that. The rest of this all came from that same Sparta script, but it's not used, so it's not important in this case. They did say in the journal article that they were including rotational energy exchange, but they did not mention vibrational, so I left that out. All right, so we can see the air species like we're talking about here. We've used the same format in the other examples, but this one has more information. But just remember, past the rotational relation, it's not being used anyway. All right, next we go into our collision model. And this is just the same method and the same process that we've used in the other two examples. The author stated that they used a variable hard sphere model, and they actually gave us these values that they used, and these values do agree with Bird's tables inside of his Appendix A. So you can look at this and you can go and verify, but all this stuff is just the same in Bird's Appendix A tables as it was in the journal article. All right, so next, in this problem, we have another file that's coming in, because in the previous two examples we used the upper boundary and the lower boundary as surfaces. In this problem, we're actually going to have a surface inside of the domain, so we actually have to describe that surface. We got to tell SPARTA in the input file where that surface is located, etc. And so the way that this is done is there's actually a file that you can read in. And so example, this one is, I've called it data flat plate 403, and I'll explain what the 403 means. And you can see in SPARTA, when you're in a 2D simulation, you have to make up the surfaces with points and lines between the points. And you can describe this rectangular flat plate in 4 points and 4 lines if you wanted to. But when you do your computations on it, it actually averages it over that line. And so if you did that, if you're looking at the top surface, you're only going to get one piece of data from that, and it's the average over that entire top surface. And that's not what you want, because there's a lot of changes that occur down the length of that surface. So what I've done here is, and you can see, it's very important that you lay it out in this way, with you got to put 400 or how many ever points you have, and then points, however many lines you have, and then lines. That way it knows what to look for. And so you see here, then we list our points, and then we come down and we start listing our lines. And the lines are listed as like, line 1 is from point 1 to point 2. Line 2 is from point 2 to point 3. Line 3 is, and then when you get down to the end, line 403 is from point 402 to 1. All right, so it's really important you do that. And so the way I've got this laid out is there is 400 line segments that make up the top surface, 1 line segment for the far right part of the surface, 1 line segment for the bottom of the flat plate, and then 1 line segment for the left side of the flat plate. And when we take our computation or data and compare it to his journal article, they looked only at the upper surface. And so that's why I discretize the upper surface so much, so we can get a lot of data points and start seeing some of the relationships. And we'll look at that more when we look at the results in a few minutes. Okay, so as you can see, I've done that with 200 line segments on the top section in this 203, and then I've done it with 800 line segments in this 803. The way I've got it run right now is for the 403, and it slows your program down extremely when you start increasing the amount of surfaces you have, because it's got a lot more computations it has to make. So just keep that in mind, how much detail you actually need. I probably could get away with less, because when I'm doing my post-processing, I'm actually doing some averaging to try to take out some of the scatter that's in there. All right, so those are our 3 files that are going to be read into the input file. So the air species, what our species is, our collision model in this air VSS file, and then our surface file, which is in this data flat plate 03 file. And you can name these as you want. It's just how you have to just call them correctly inside of your input script. And another thing we'll talk about that in a few minutes. So let's go into the input script and start looking at how we laid this out. And so, like we talked about, it's the 2D flow around a flat plate. We initialize it the same way as we did the previous problems, even though they were 1D, because in Sparta you have to do either 2D or 3D. All right. So here, next we look at our boundaries, and here we got our boundaries are O, R, and P, and O is an outflow, P is, or R is spectral reflection, and P is periodic. He discusses in the article how the x-axis or the x boundaries, positive and negative, one is the inflow, one is the outflow, so that's why we use O for the outflow for x. Then he talks about how the upper and lower boundaries are going to be spectrally reflective, and so that's why we use that call for that. And then last, we use the periodic for Z. He didn't discuss that in the article, but since it's a 2D problem and Z is really just being defined because Sparta forces you to define it, and so we decided when periodic means that when something goes out, something else will come in, so that'll just keep everything balanced out to where it doesn't affect the simulation. All right, so next we created the box. Here we created the box instead of going from 0. I took the X domain and I shifted everything to the left. That way, when we place our flat plate in, we're placing, I guess, the leading edge, the center of the leading edge is going to be at 0, 0 on the XY plane. And that's what they discussed that they did inside of their article. And you can see in their images, if you pull up the article and read it, where they did that. So here's where I define it. I'm using the X domain. I've shifted it left, and then I took the Y domain and just split it between above and below the X axis. That way it would be centered. And then again for the Z axis, since this is, or the Z dimension, since this is a 2D problem, we still have to define the Z, and I'm just defining it with some number to that's on either side, and that's the way that Sparta talks about in the manual to define it. They talk about in the manual like maybe 0.5 and 5, or negative 0.5 and 0.5, but this is what I used, and this really appeared to work really well. So next, when I discretized the grid, how we were talking about, how they talked about inside of the journal article, I end up getting 360 grid widths in our grid cells in the X direction and 410 in the Y direction. And so let me check now what I was, yep, it is. So you end up with a total of 147,600 cells. And so, like we talked about originally, this is like, this take 30 to 45 minutes, maybe an hour to run. It takes much longer than the previous two examples because there is so many more grid cells. Next, talked about rebalancing, how we balance the grid the same way we've done in the previous examples, and then we looked at rebalancing the grid. He talked about this in his journal article, so I looked into it some, and this is the line of code that'll rebalance it. So every 4,000 time steps, if the processors, I believe, or if the cells are out of balance more than like 30%, then it'll rebalance everything and start again. So it just keeps you from getting too unbalanced. And this is the way, I believe this is the way he said he did it in the article, but it's performing that function. So next we take a look at our gas and species mixture, and we're calling it in the same way we've done in the other examples, where we use the species command, then we say pull this file air species, And then we're just going to say, okay, give me the information for the one that's ID'd N2 in there. And we looked at that a moment ago. So next I'm defining what the mixture is like. And so I say gas, the mixture is a gas of N2. I'm calling my mixture gas. It's made up of this species N2. The velocity, the V stream velocity is going to be 1504 meters per second X direction, like was discussed in the article. The temp is going to be 13.34 Kelvin, like was discussed in the article, and N rho is going to be this 3.7 e to the 20, as was discussed. All right, so F num is going to be calculated based off the desired 10 particles in each cell and the N rho amount above that's shown in the mixture. And I actually have added that to my report, so I can show you that calculation here. And so this is how you calculate what your F num is that you're going to put into your simulation. All right, so you can see you've got your N rho and you got your volume, and this is that where you multiply by 1 in the z direction, even though it's because you don't have a volume because it's really a 2D problem, but you have to add that when you make this calculation. So you just multiply by 1 for the z direction, and that works all out to where your F num is 9.29 e to the 12. Okay, so if we come back over to Sparta, you can see where I've got that. So I call out the F num 9.29 e to the 12. So that right there is going to create the particles that make 10 particles per cell. And so whatever the 10 particles per cell is, that's what we should have when we start running our simulation. We'll have a lot more than we had in our previous examples, and that's another reason why everything is moved. It takes so much longer to run this one. All right, so next we look at our gas collision model. So just like before, we're going to use the collide command. We're going to say VSS because I believe you always have to call it VSS, or that's like the main command that tells you to do this. And then we're saying we're going to use this mixture that we defined as gas, and then we're going to use our collision model that's defined in the air.vss file. And we know that our collision model that we have described in that file is the variable hard sphere model. So even though you see VSS everywhere, don't be concerned. We're actually running the variable hard sphere model because that's what's defined in here. Next, this is something I had to do some research on, and this is where you actually can turn on the vibrational energy exchange or the rotational energy exchange. And so you go to the command is collide modify, and then I use rotate smooth, and that turns on the rotational energy exchange. And then I don't believe that vibrate no is needed, but I put it in there anyway. That just says we're not considering vibrational energy exchange. All right, so we have the same fix here. I'm not exactly sure what this does, but I think it has something to do with how it lays the particles in there initially. I've seen it in every example. All right, so next we get down to our surface geometry and the collision model for the surface. And we've discussed the collision models earlier for our surfaces, but that was for when our surfaces were a boundary. Now we're actually reading in a surface. And so we're going to read in the surface, and we said data flat plate for this. So that's our surface that we had, our file that described it with the points and the lines. And then when I say translate, that's how I can move it somewhere. So I'm saying put it at 0, 0, 0. And so if I wanted to move it forward or backwards into the flow, I could just say maybe 5, 0, 0 or 0.5. But that's how you would move it one way or the other. So if you wanted to raise it up. Now there's also commands for rotating it. There's actually commands to move it during the simulation. So this is just the basic of it. I'm going to read the surface in. I'm putting it like the front point right at the origin. All right. So next we're saying surf collide. We're saying surf 1 is diffuse. 290 degrees, because that's what it said this was kept at, and we're using fully diffusive collisions. So all the collisions are going to be diffusive in nature. All right, and this would just say surf modify all collide one. So I'm just saying all my surfaces are going to do this, are going to have this 290 degrees, and they're going to have diffusive collisions. All right, next we talked about the compute and the fixes and the dumps all in the previous examples. So none of that's changed really. The only thing that has changed here is when we get down to the next section, now since we have the surface in there, we're going to want the information off of the surface. And so when you go to compute, there was a whole bunch of other surface computes too. And so this is 2 lines I use to compute properties off of the surface. And so like this one first tells you where your X and your Y is, this compute S geometry. So you'll have your X and your Y inside of your data that'll come out, so you can actually like plot versus X or plot versus Y if you wanted to. All right, next you have these where I'm calculating some properties like pressure. I believe this is shear in the X, shear in the Y, shear in the Z. Then we got the total energy flux and the kinetic energy flux. So those are some of the things that I calculate on that surface. And like I said, this is the flux over that little area of surface. And so I think all that is pretty clear. That's new though, so it's like something, and you have to like tell it what you want, and you're telling it, yeah, I'm gonna do it on all the surfaces. So when you get your information, it'll be over the whole, like you'll have 403 pieces of information for each one of these variables, and then you got to determine which ones you want when you do your post processing. All right. So same thing with the dump, and the data file. So now, like we're saying, I can show you right here. Now, when you run it, you're actually at the end. You're going to have a surf data file, and you're going to have a grid data file, because you're pulling this information up here, all these computes on the grid, and then you're pulling the computes on the surf. All right. So you're making another dump on the surf, and you make the dump on the grid. Okay. All right, statistical output just like before. That way we can see what's happening, our number of particles, etc., collisions. Then we got our global time step. This is what they described in the journal article. Is this 3.102 e to the -7? This is something that I'm not doing, but it's where you could dump an image. There's simple ways to dump an image and make like a little GIF if you wanted to with a bunch of images. I'm not worried about any of that right now. All right, so next we have our transient run, and just like before, we're gonna use the undump, and this just basically says it tells me I don't want to dump the information from the transient run. We're not worried about that. All right, so next we go down to the steady state run. Right, and so you're gonna run. This program's gonna run 8,000 time steps. It's not going to take any data, but it's going to keep progressing. And then once we get to this last part where we're going to run 4,000 in the steady state, that's when we're going to start taking data. All right, so here's where I like in the other ones, I think we could probably just put this stuff down in here if we wanted, but it's not that crucial. And so we'll have get rid of this stuff up top, because we're really only doing this down here. We're unfixing and then refixing. All right, so here we're going to refix, and what I'm doing is I'm taking averages over 1,000. Over 1,000. So every 1,000 steps, we're going to take an average, and then we're going to dump that information for the surface and for the grid. And so when it's all said and done, I'll have four surface files and 4 grid files that'll be an average of 1,000. So our last 1,000 would be the probably more accurate, but I was doing a running average on this. It appears that I've taken it off of this one, but when I show you the data, you'll see that it's still reasonably good. Okay, so I think that covers it all on this part. I think now we'll look at, I got another one running up here now. So let's go back here to Right, so we'll do it like before. We'll open in the terminal, and then like before, MPI, run, number of processors you want, where this um, program to run it is in your files, and then the name of your input file. And so you run it. This, like I said, this is a lot slower. And you can see like the number of particles is way higher than we had before. The number of collisions and everything is still building. And so you'll see that it builds up and eventually it stabilizes. This takes 30 to 45 minutes to run to 12,000. Okay, so I guess let's go over to the post-processing. Oh, well, actually, before we do that, let's look at these two files. So here's our last surface file. So you can tell, you just like before, you have to look at what your inputs are and then see what these are actually going to be in your inputs. And the first few are the geometric inputs. It tells you, that's telling you your X and your Y and your Z locations. And then the rest of the data, that all those variables and or parameters that we were trying to get off of the surfaces. And so that's how you do that. You just got to really like look through what you asked for, look through what you got, and see that they make sense. All right. Next. It takes forever to load, and that's because we have 174,000 lines. And so this is, like I said, no different than what we did last time. Just you got to go take your time, go through there, have your Python script, open it up, and make a CSV file out of it so you can look down and look at them and just look at things like, oh, this is probably number density or something to do with density. It's like real high. And just like see if things like this one obviously is like a temperature or a velocity. You know, this is the velocity because that's what we're talking about, 1,504 meters per second. So you just got to take your time and look through that stuff. All right, so now let's go over to the post-processing. And I'll run a couple of programs. It might take a second, but I'll run a couple of different data sets. So the data set from the one we just did should look something like this. And what I did was I took the journal article and I found a program that my professor suggested that'll let you actually like pull the data off of an image. And so that's what I did here. And I believe this data set is if I use like a running average over that 4,000. But you can see this is what the author had for his results, and this is the upper shear stress and all these, like he's got all these images inside of that journal article when you pull it up. And then you can see like, so this is only on the upper surface, and you can see that it's flowing and I'm really close. And when I did this data, what I've got this program doing is it takes the first data point and the last data point, and then it takes every 10 data points in the middle. And when you decide which data point you're going to plot at that 10th one, you take the average of the two on either side of it and that data point, and that's what's actually plotted here. When I just plot every data point, it's just so thick because it's got so much little oscillation in it from the statistical scatter. But as you can see, it matches really well with what the author presented, and his results that he presented matched really well with experimental data. So all looking good. The heat flux is the one that's probably got the more issues. It's just a little bit off. It's like dead on for the final 2/3 of the plate, but the first third it's a little bit off. All right, then we can see we got our rotational temperature contour plot, so that you can see, and like this is when you look at it, this is what you would expect the flow to look like on this velocity contour, and you would expect the temperature to be looking this way as well. All right, so what I will do is I ran another one with Let me pull it up and make sure I'm not telling you no lies. Just be patient with me. So I made another run with the 800 the 800 surface, like discretized the upper surface into 800 units, and then I ran the whole program out to 100,000 time steps, and I used the same averaging system that I used for the last data set, but this shows like if you run it longer, and like I took a running average over the whole time, like all 100, well, I skipped the 8 or 10,000 at the beginning and then did a running average over the rest of it, and you can see it really smooths out and starts looking just like what what the authors had done in their work. And there's still some deviation here. I haven't quite figured out the deviation here. And if you look in the journal, it's this, when they start talking about the heat flux, it looks a little bit like maybe there's not an apples to apples comparison. This is what when I do just the kinetic energy, it matches up with what they had for heat flux. And then they have, if I add the rotational, like the total energy to it, it actually is really close to what they have for their other plot in there that's supposedly another program. So you take a look at it and try it and see what you think. But I think the results match really well, and I'm very pleased with this one. And so I think that's the end of the discussion I'm going to have here. I think everything has been described enough where you can run this simulation. I'm going to put the journal article in the description. That way you can go and pull it up. I was able to pull it up myself without having to, join anything. So I'll put that in there. Like I said, I'm Aaron Wallace. If you have any comments or questions, feel free to ask. I'll try to do my best to answer them, but I am still very novice at SPARTA and the whole DSMC process in general. But like I said, I'm Aaron. I'm trying to work on a project for my master's, and have a good day. Thank you.